I put the a web page that I went to visit. And on the left, I'm using a tool called Fiddler. It's a simple HTTP proxy. Allows me to see every single request that's actually happening. So I went to go visit that page, and as you probably saw real quick, calc.exe popped up. That's the most common, obvious proof of concept you can kind of show, just to show that you can execute something. Now, in Fiddler, on the left side, or your left, one page came down, exploit5.html. And if we look at that content, which is right here, I didn't use script fragmentation in this example. So this content right here, where I'm circling with my mouse, is what came down. I'm actually, just for the proof of concept, executing a local calc.exe. I'm not going fetching anything. But it's very obvious that with this code, this CLS ID, and multiple other things, that I'm actually trying to do something malicious. Larger chunk of code here. So let's try to do the same thing. This is demo 2 with script fragmentation. So on the right side, again, is a web page that's using script fragmentation. It's a demo, so I've got some buttons that make it obvious that I'm doing script fragmentation. And then on the left side is Fiddler again. So what's happening? What's happening is that it's going to fetch multiple offsets and asking constantly for the next 3 bytes, the next 3 bytes. And for debugging purposes, and so we can see what's going on the right-hand side, as XML HTTP request is constantly asking for those next 3 bytes, I'm showing that file total size is 246 bytes. The end of file has not been reached. And you can see in real time right now, although it's a movie, the text and those 3 bytes that are constantly being sent down. We finally hit 246. Calc.exe popped up on the left-hand side of that screen. You can kind of see it over here. And let me pause the movie for a second. And so what we just saw was probably, 246 divided by 3, whatever that is, like quite a number of requests. So the negative thing here is that with every 3-byte request, we have like 100 bytes. That's the headers coming down. So we're asking for a lot more data, but we're asking it for in smaller chunks. And so it's supposed to be a lot less obvious. But if we're to look the same way we did with the previous example, what we're actually looking at here, my mouse again being circled in this particular area of the content being transferred, file size 246, end of file 0, text :CO4. Imagine some content analysis engine trying to look at that. They're not going to know that that makes any sense, and they're really not going to know what to do with that. So again, no script fragmentation. I ran that simple 100-byte design bug of MDAC through VirusTotal. VirusTotal is always just a real basic way. It's not to say that any of these AVs wouldn't catch it a different way, but it's one of the first kind of ways to check how well they did. And the majority of engines just caught that simple 100 bytes of information to say what it was, what exploit it might be, MS06-014, that is the MDAC. So simple. With script fragmentation, it wouldn't have caught it. Obviously, the decoder comes down, and no malicious code comes down. It's going to be asked for it in smaller bytes. So AV won't detect script fragments. The initial page will hold the decoder routine, and then and nothing else. The file on disk will never change. That cache that we talked about at the initial start of the talk, that just held the decoder routine. It never changed. Remember, the DOM maybe changed if you weren't using eval. If you were using eval, it didn't change at all. But the thing is, don't touch disk, don't have it change at all, and in memory, be as specific as possible. It's the end-to-end argument. I mean, that's where the most intelligence is happening, right? It's be as close as you can into the DOM memory. So no substantial content can be scanned as malicious. And with a decoder, so the first thing that comes to mind is, all right, great. So we were catching deobfuscation routines, and that's how we were basing our signatures. I'm just going to try to catch generic decoders. Even if you use, constantly change them, I'm going to start making those signatures for those. Well, it's the same way. I can make them polymorphic, and then what I'm going to start to do is I'm going to try to use as little custom code as I can. There's tons and tons of libraries that are doing this exact same thing. Web 2.0 good applications are doing the exact same thing script fragmentation is doing, which is fetching content from servers, and they're going to be fetching content from multiple servers more and more and more. So you've got Prototype, Dojo, Yahoo, lots of other libraries that you can use, and use that code to go fetch these little bytes. Don't make your decoder custom. I mean, that's the number one mistake a lot of attackers will do. The more custom code they use in anything, malware, malicious web pages, the more obvious it is that we can center on who it is, their technique. Be generic. So use the libraries, less custom code, the harder it is to detect. And at the same time, the JavaScript engines that a lot of gateways are using, can't hold that much state. As I stated at the beginning, almost throughout the entire industry, if you're at the gateway and looking at the application layer, you have under a 1 millisecond to look at content. You really you can't hold that much state. A lot of the public implementations are faulty. Billy Hoffman did a talk in 08 at Black Hat. He just showed some of the more public tools and showed how they didn't implement various functions and how we could bypass them. I mean, it was just an example of how a lot of the research tools might be lacking, but the private tools are obviously a lot more well implemented. So from the attacker standpoint, it's victory, right? Script fragmentation, very successful evasion technique to evade both the desktop, the traditional desktop, as well as what the current gateway is looking at in terms of that is still what the normal technique is to send the content all the way through. That's what they're focusing on. They're not yet focused on Web 2.0 applications or attackers using Web 2.0 functionality to use AJAX, in an AJAX-y fashion to send down content. So from the perspective of the attacker, it's very successful. So my final remarks: future defenses, mandatory slide. Sure, better JavaScript emulation, right? This isn't going to help the multiple connections going out, but this is going to be necessary for the other type of future defenses. One way that we combat it and other people combat these multiple connections is perhaps the protection isn't at the gateway. Something based off heuristics triggered an alarm. It goes back to somewhere in the cloud, some central office somewhere, and it gets fed through multiple VMware, multiple Zen machines, looking at what's happening in the DOM memory, looking at what's happening on disk, any changes, looking at what's happening after the fact. Great. You were able to transfer your content from the malicious web server to the browser. But were you careful? How careful were you with your exploit after that? Really, did you use common functions, URL download to file, or something that would be obviously hooked in most kind of desktop research tools? So some type of gateway worker gateway defense combination is going to be used more and more and more, making use of the cloud. So I have under a millisecond to look at the gateway. All right, it got passed. This happens with a lot of DOSing attacks. It got passed. But you know what? We're gonna feed it off somewhere else, and we're gonna catch it on the second one. So it's kind of some type of feedback loop. Gateway client defense combinations. Well, the gateway has a certain amount of intelligence that the client will never have in terms of multiple connections. The client has intelligence that the gateway might never have in terms of bringing that information together. So perhaps functionality within the communication of both the gateway and the client. The other perspective is that right now most desktop AVs, some of them are starting to do some like we did with host-based intrusion prevention systems, some type of exploitation detection in memory. This shouldn't happen, hooking certain instructions, hooking certain functions. But one of the simple things that they could start to do, perhaps simple, even though the APIs really aren't available in all browsers, is to inspect the DOM and the JavaScript engine. A little bit more hooking in there. If they have a closer view of what's actually happening, not just hooking eval and document.write, hooking manipulations of the DOM, Um,